Today we're going to discuss the two main types of action potentials that you can record in a electrodiagnostic examination: the sensory nerve action potential, or SNAP, and the motor nerve action potential. You're very familiar with these, I'm sure, already. The SNAP looks something like this. It may have an initial positive deflection, big negative deflection, dip down below baseline, and then gradual return to baseline. That is a fairly typical looking SNAP. It might be narrower if you tend to do your studies on a faster sweep speed. The motor nerve action potential looks a little different in that it should not have an initial positive deflection and generally assumes something like this shape. So there are a few fundamental differences between these two types of potentials. We'll start with a little bit of a seeming digression. I have two images here from New York City. The upper image is a statue of Beethoven located somewhere in New York. The bottom image is, of course, the Empire State Building. Now, if I were to give you the task of trying to locate these two places in New York City, which would be easier to find? Obviously, the Empire State Building would be far easier. The height of the Empire State Building is over 4,000 feet. The height of Beethoven statue is probably 3.5 feet, or a couple of order of magnitude difference between the two. So you could be standing in downtown Manhattan and readily see the Empire State Building. You could search all day long and never find Beethoven. What does that have to do with this conversation? That's my analogy to the sensory nerve action potential, which is Beethoven, and the compound, motor unit action potential, which is the Empire State Building. There is a huge order of magnitude difference between the size of these two potentials. The sensory potential is measured in microvolts, and if you can draw that, that's represented by the mu symbol, microvolts. And a microvolt, micro in the decimal system, is 1/1,000,000th, so that's a decimal place and several zeros. The motor nerve action potential is measured in millivolts. And a millivolt, represented by MV, is 1/1000th of a volt. Now, if you ask yourself how many millivolts, how many tiny microvolts are there in a larger millivolt, I'll let you do the division, but you would divide microvolts into millivolts, 1/1,000,000th into 1/1000th, and if you do that math, you end up with 1 millivolt is the equivalent to 1,000 microvolts. I know everyone knows that, but it's sometimes easy to forget, particularly on modern EMG machines that set all the settings automatically. You click on sensory nerve action potential and all the gains are automatically set. Even though those potentials look similar when you record them on a modern EMG machine, remember that underneath it all, they're hugely different, as different as Beethoven and the Empire State Building. The reason for that is probably obvious to all of you. And I learned this technique from Frank Netter. In a sensory nerve potential, we are measuring the action potential, or the depolarization of this tiny digital nerve by the ring electrodes on the finger. Very, very small structure, very small electrical generator. In a motor conduction study, I think that's 6 fingers, but we'll go with that. This is my abductor pollicis brevis, and I'm going to pick up over the muscle. The entire muscle is an electrically active membrane. The entire electrically active membrane generates an action potential. It's a relatively huge structure compared to the little digital nerve we're measuring, the sensory nerve action potential. Therefore, a very tiny microvolts potential compared to a very large millivolt potential. Now you might say, why does that matter? The machine makes the setting for you. You don't really have to remember that. What practical use does that have? It has a little bit of a practical use. Again, if I set you loose in New York and said, go find the Beethoven statue, you could wander around for days. If I set you loose in the EMG lab and you were a little anxious or had a particularly anxious patient, or maybe your technique is not quite up to snuff, or your machine's not working quite right, the sensory nerve action potential will be inherently more difficult to obtain. So as a general tip, if you are going to include motor nerve and sensory nerve conduction studies, why not start with the motor unit study? Why not look for the Empire State Building first? Very easy to get, much easier to elicit than a sensory conduction, and it gives you a chance to get you at ease, get the patient at ease, make sure your machine and equipment is working properly, instead of chasing after the much smaller potential. So a little bit of a practical application to that size issue. The other major difference, and we'll end with this point, is the onset latency for motor nerve action potentials. We measure that onset latency at the initial negative deflection from the baseline. For sensory nerve action potentials, we measure that initial deflection from peak. Now, why would anybody devise two different methods of onset latency? It makes a difference in what you're seeing in this potential, or what you're actually measuring. And we'll talk some about this in more detail in subsequent videos. But recall, this motor unit potential is the algebraic sum of a whole lot of tiny action potentials that are summed together to make this waveform. So you're really measuring the fastest conducting fibers here with the onset latency. With the sensory latencies, you are measuring a different population. You're measuring a population that's sort of in the middle range of conduction velocity. So a little inherent difference. So why set that up differently? I think the reason is historical. And if you think back to ancient history, before the time of computerized EMG, EMGs were done on oscilloscopes, and they were done on oscilloscopes without screen capture. So kind of like the old Navy movies where the sonar operator sees the blip, and the blip's there for a second and it disappears. You would see a tracing of this sensory nerve action potential, which was a very small potential, briefly phosphoresce across the screen, very rapidly fade, and the operator had to determine the size of that potential and also the latency of that potential in a bit less than a second, which is why historically we chose to use peaks instead of onset. The peak was just easier to see, particularly in a smaller potential. So that's it for the real basics of SNAPs and motor unit action and motor nerve action potentials. Sensory much smaller, motor much bigger, much different electrical generator generating that size, and the onset latency for the motor is from the onset, and the latency for the SNAP is peak.